Greetings! What do we have here? We have a Tektronix TM5006 power frame. Power frame for what, you say? Well, Tektronix came out with this in the early 80s, I think, and it's a modular test system. You can plug modules into here and build your own test setup. They had many modules available: power supplies, frequency counters, signal generators, that sort of stuff. This was the successor to the Tektronix TM500 series. It's fully compatible with TM500 series modules, so you can use all of those, giving you a really large choice. But it doesn't work the other way around. You cannot put any TM5000 series modules into a TM500 power frame. And I'll tell you why. As we said, it takes 6 modules. 6 single width modules, I should say, because there are some that are double width. But you got 6 sets of edge connectors here, identical. And then next to it, you got 6 sets of smaller edge connectors, also all identical. The big green ones are compatible with the old TM5000 series. They supply power. They can be pre-wired in the back to connect things, to hardwire certain modules together, so you don't have to use patch cables to connect them. The smaller connector, and this is the main difference between the 5000 and the 500 series, is they give you GPIB interface capabilities. So basically I shouldn't say all, but most of the TM5000 modules are GPIB enabled. And the reason they won't fit into a 500 cabinet is because 500 cabinets or power frames don't have these connectors, and so it physically won't go in because the smaller edge connector on the module won't slide in. But anyway, that's the general outline of what it's basically a power supply module. It's very similar to modular's music synthesizer, actually. But let's take off the covers and see what's inside. So here's the rear half or third of the instrument, which is a large power supply. Starts out with a transformer, being linear because it does supply AC voltage to all of the slots. But then it uses a switcher over here. We'll focus in on that. That supplies a bipolar, 20 some volts, also to all of the modules. It's got a pair of complementary power transistors for each slot. There's 4 pairs here, 5th pair here, and another pair hiding behind, except the one hiding behind is using larger transistors in a TO3 package. And the reason for that is that this cage offers a high power output on the 6th slot over here. And yeah, that's about it for power distribution. And really the only thing we can test on this is does it turn on? There's a fan, so it does a fan run. And then there's test points in front that we can measure to see if it's supplying the DC voltage or voltages. There are no test points for the AC outputs here, but if the DC voltages are present, there's a very high likelihood that the AC voltages are also present, and we won't find that out until we actually test this with a module. But let's have a look at the tests prescribed by the manual. Anyway, here you can see most of the linear supply. Let's see if we go down further. That's the switcher part, which supplies us with voltage over here. And the little ribbon cable here is the GPIB interface wired in parallel with all of the smaller connectors on the back. And it comes out, it terminates with a GPIB plug on the back, which is this. And that's about, yeah, that sums up what the box does. So there's actually 3 DC voltages this generates. Okay, so test 1 is, does the fan run? Not if it isn't plugged in. Okay, take 2, test 1. Does it turn on? It does. Next test, we're supposed to check the 8 volts. Well, the 8 volts is supposed to be 8.2 volts actually. So let's see what it says. How do I do this without shorting anything? 8.2. That is adjustable if it was off, but I think 8.2 is pretty good. Then we have plus minus 26, which do have a tolerance of 0.7 or of 800 millivolts to either side. So let's see, the first one is it's slightly below the tolerance, or above the tolerance I should say. It's supposed to be 26, but it's 25. But these voltages don't get used directly by the modules, but are rather regulated for whatever voltage they need on the board. So I think that's okay. So again, this one was negative 2515, positive 2515. So magnitude-wise, they're both a little low, but they're perfectly symmetrical. So I think that's sufficient. And we'll just say this passed. Well, that was exciting. So let's actually bring our first candidate into view. PS5004 precision power supply. Come on down. So this is what a single width module looks like. See the connectors, the massive power connector, and then the smaller GPIB connector, and a bunch of dipsticks for you to set the GPIB address on it. So let's slide it in and see what happens. I'll just put it anywhere. Doesn't really matter where. And there it is. So let's see what it does. Where's the power switch? Over here. Now these things need to warm up. And the interesting thing on this one is that the display, even though it has a CPU inside that reads what you're selecting, it's actually a multimeter. So this isn't the processor just displaying what number you entered, but rather it's monitoring the outputs. It's measuring the outputs and showing you what those are. This takes some time to warm up, So let it warm up for a little bit. Well, we gave it about a minute to warm up. It's kind of stabilized on 20 millivolts. The way you select the voltage is it's got a rotational encoder right here that works in one of two modes. In coarse, it increments by 100 millivolts, and in fine, it increments by 1 millivolt. But I played around with it, and the rotational encoder, even though it does work, it doesn't work really well. Let me demonstrate. You can see it's not doing anything. Now, if I turn it more rapidly, then it works. And it's right now it's in the 1 millivolt range, so we can get it down. Get it down to 0, kind of, but when I turn it slowly, nothing happens. Well, it did happen actually. 1, 2, 3, 4. Oh. Yeah, it is definitely intermittent. Now, the way you get to the coarse setting is you click it. And now you can see it's increasing in 100 millivolt steps. So that all looks good. But you got to turn it rapidly. Now, frankly, I do not know if it's supposed to be that lazy. I suspect it is not. So I've seen rotational encoders do this, but normally what will happen is when they go bad and the internal contacts go bad, it'll start, let's say you're increasing a value, and all of a sudden in the middle it'll decrease the value for a couple steps and then go back. This one just acts lazy. So what I'm hoping is that maybe it's just dirty and I can clean it up, because early 80s Tektronix, they're probably using some whiz-bang encoder. I've looked through the parts list, and on a quick search I haven't found a replacement, but hey, the first thing we got to do is take this thing apart so we can get to the actual encoder inside. Side panels came off pretty easy. Then this is the digital board we were looking at. It's got a Motorola 6802 8-bit CPU, ROM, RAM, glue logic, a TMS9914 GPIB controller with line drivers, and yeah, that's about it. The other side shows us the underside of the analog board. So if you were to had to change components, you'd have to remove the board, but it looks like all the trim pots were conveniently mounted on the solder side. So that's not going to be a big deal. The evil encoder is sitting right here. And my guess is that we're going to have to disassemble this whole thing here to get to the encoder. Now again, I said I've experienced bad encoders, and if at all possible, get a replacement, because they're very, very susceptible to dust, dirt, and corrosion. But on top of that, in order to prevent that, they're usually hermetically sealed. Well, if the hermetic seal fails, then the dirt can get in, but whatever cleaning solution you try to get in there won't get in, because it took the dirt years to get in, and we don't have years to wait for this. Either way, I got to get that encoder out and figure out, how we're going to clean it. But first, I'm going to have to figure out how to take this thing apart. It's very puzzle-like, interlocked. Anyway, let me have a look at it. Well, I stared at it for a while. I could not figure out how to take this thing apart, so I did the unthinkable. I read the fiddling manual, and there's the results. As you can see, it came apart cleanly, and the manual didn't lie. I did exactly what they asked me to do. But here's the rotational encoder. I'm going to have to remove it from this carrier board, desolder it, and see if there's any way I can take it apart once it's off this board. So after some more serious thought, I decided not to remove the encoder from this board and tempt myself to take it apart. There are lots of small parts in here. It's a quadrature encoder. I've seen others. When you open them, parts start flying usually, and if I destroy this, I basically destroyed the whole module. Kind of works, which is better than it not working at all. So I'm going to first drench this in alcohol, and I think the only way in is where the shaft and the mounting thread, there's a gap here. Put some alcohol in it, maybe soften up things, and then spray it with contact cleaner and see if that makes any difference. Well, I got a deoxide bath. I exercised it. Oh no. Unfortunately, there's no quick and dirty way to test it. I'm going to have to put back together the whole thing and see if it made a difference. Probably didn't. But at least I had a chance. The front panel was cracked, the plastic. Like somebody levered it, put his finger here, his fingernail here, trying to pull it out and cracked both corners. But at least I super glued those back, and it's good as new. Well, everything's put back together. But before we look at the results of our cleaning the rotational encoder, let's see how the voltage generation in this works with this meter as a reference. Now I compared this meter to the meter that's my daily driver, this guy, and they're the same, but this has more better resolution on it. So let's see. Now remember, this was dancing around, but note the voltage. I mean, this is hooked up here. It's supposed to be 0, but this tells us that it's seeing 0 volts coming out, and that something in here needs to warm up. I thought it was a power supply, a voltage generating circuit that needed to warm up, but it obviously isn't, because it's dead on at 0 volts. So we got to give this a little bit time, which indicates to us that the DMM in here is the one that is doing the dancing around and not the actual voltage supply. Oh, now it's going to make a liar out of me because I didn't turn the output on. But with the output on too, we can see that it's still sitting at 0. So let's give it a few minutes until this display, I mean, it's already kind of stabilizing, and since this matches the fluke meter, this is the true output coming from it. So let's give it a few minutes to warm up. So it's warmed up. I moved the module over to here because I've left off the side panels, which you can kind of see here. This is the digital board and the analog boards over here. But this gives me access to all of the pots over here. I did some preliminary voltage adjustments off camera. But where we're at is basically I trust this voltmeter. So let's see if we can adjust the DMM on here, and then we'll look at the results of our cleanup on the rotational encoder. Okay, so we're going to adjust the DMM 0. That's the wrong direction, because I want the two voltmeters to agree and get them as stable as possible. Okay, except for the sign, they are in sync now. So now to the rotational encoder. As I kind of predicted, it didn't make a big difference. It is worn out, and so is the button when you press it. And the funny thing is, this is actually a dual rotational encoder in there. Looking at the schematics, a rotational encoder basically has two outputs, the two phases, a phase A and a phase B, but this one has a phase A and B for the coarse adjustment and a phase A and B for the fine adjustment. So there are two separate physical encoders in here, and when you click the button, it toggles between putting it in coarse mode and in fine mode. Why they used an encoder with two outputs, I'm not exactly sure. It probably has something to do with the resolution of the encoder. But anyway, yes, things didn't change greatly. One thing that I found was, let's see, right now I think we're in fine mode. Helps turn the output on. Oh, I adjusted it to null without the output being on, so let's go back down here again. Oh, that's still good. So my tests showed that basically in its current state, when you're in coarse mode, it only responds to every fifth or fourth click. Now, if it was always dead on, only did it every fifth click, I would suspect the hardware, but it varies. I've also seen it respond after 3 clicks, which definitely points to something being physically wrong to the encoder. So you basically have to sit here and turn it rather quickly. It's in coarse mode right now, so we're going up in increments of 100 millivolts. But yeah, 1, 2, 3. See, this time it did it after 3 clicks. 1, 2, 3, 4, 5. This time it did it after 5. I looked around and that encoder is not readily available. So let's just kind of twirl it and see how accurate the output is. So it's off by 5 millivolts at 10 volts. And the maximum is 20 volts on this. I can probably fix that, the millivolts that's off, if I go through the full calibration procedure. But I'm not going to do that just now. I want to see if it's accurate enough for benchtop testing. I'm not designing any precision circuits with this. So there you go. It is maxed out right now. we can switch it to fine. So as you can see, fine, it is basically, it's 2 millivolts off at the top of the scale. And as I mentioned, for benchtop, mostly for benchtop testing of equipment and light design work, that's good enough. And finally, let's see if it can supply the advertised 300 mils max. Now we can see that on the load it's in constant current mode, but the voltage is off. Not hugely off, but it is off. I'm going to trust this and this, and we're really mostly interested in what the current value is going to be. And that's set, this is set to draw 300 mils. So let's turn it on. And it's drawing 300 mils. Does make the display a bit unstable. The voltage droops on this one. But yeah, it's basically in constant current mode. Even though the funny thing is they're both lit. That's not right. Constant voltage and constant current is lit. So what happens if we turn off the output? Then it goes back to constant voltage. I guess that is correct. That's the way it does it, but we can see that the current matches. The output current matches well, and the voltage drop still is negligible for its intended purpose in my lab. So finally, let's see what happens if we try to draw more than 300 mils. And we do that, the cursor is set to the hundreds of milliamps. So let's go up to 400 milliamps. And basically it shuts down, as you can see. But it comes back. And if we go to tens of millivolts, it shuts down too. The minute we go above 300 milliamps. So it's working, and it's current protected, so it's not going to self-destruct if you hook up something to it that draws more than 300 milliamps. So it should be safe to use. So to sum it up, it is usable for now on the bench. Not so much for design work as for just testing stuff. Whenever you're in a situation where you need a quick 8.6 volts at 200 milliamps, it's ideal for that. If I ever manage to find a replacement encoder for this, I will replace the encoder and then go through the lengthy process of properly calibrating this. But for now, welcome to the family. Thanks for watching. Please like, subscribe, comment, share, and click whatever other buttons there are. And we'll see you next time.